Okay. All right, it's my great pleasure to welcome Dr. Janice Coen today to our seminar. Janice got a degree at the University of Chicago. She's now a project scientist at both UCAR, which is in Boulder, Colorado, and at the University of San Francisco. Janice has done an enormous amount of pioneering work in wildland fire research. We have, in our topics and seminar classes, have read a number of her papers, and so the students should be very aware of a lot of that. She's designed a couple of numerical weather prediction wildland fire behavior models, developed data assimilation methodologies, and scientific programs to integrate various kinds of data into fire detection models. She's investigated heat release from buildings that are on fire and their effect in wildland fire situations. Her background in meteorology has produced really interesting and exciting case studies and stories about how extreme events in meteorology and weather affect wildland fires, channeling, fast flows, strong flows, eddies, all kinds of turbulent structures. So today she's going to tell us about her latest work and some historical work. And so I welcome Janice and thank you for agreeing to talk. So go right ahead.
Thank you very much, Kevin, for that generous introduction. I'll get you your $20 later. Now, I guess with inflation, it has to be $50. I think my reintroduction to Florida State arose with some interaction with Kevin in a book he edited, and it started our discussions, and I became more interested in becoming more involved with the geophysical fluid dynamics educational community, because I think there's some important roles for you in where we are and where we'd like to be with wildfire modeling. My work here combines results from a number of projects over the years, most recently sponsored by the California Energy Commission due to their interest in wildfires ignited by the electrical grid and how these have been changing over time and might change in the future due to changes in climate. Some of the work is sponsored by NIST, which is very interested in the impacts on the wildfires on communities, the National Science Foundation, my own institution, and NASA in terms of implementing the remote sensing sources to this problem. As I wrote my abstract, I was thinking of the background of this project, and it's to investigate and predict large wildland fire behavior. I was just going to give a little introduction how we got to where we are. That is, being an interdisciplinary field supported by computational models. The newer generation of models that we use are very different from the ones that have been used for decades in the past, that they combine some sort of computational fluid dynamics model with some package that parameterizes wildfire behavior. So I'll describe what I'm using and what it can and can't tell us about some of the case studies we've looked at. A key aspect of work these days relies on remote sensing data from satellites, but many other tools are coming on board. That is, constellations. Of course, we have aircraft observations, but also UAS and how those are integrated into the problem. Look at how we're using it for some applications, like what we understand about these exceptional wildfire events, some of the phenomena in them, how we're developing forecast tools, and how these kind of our lack of understanding about some aspects of meteorology combined with these extreme wildfire events to cause impacts on the electrical grid, and some of the what we now know are $5 billion events. So we'll look at some of the case studies and look at some of the limits to our knowledge that are holding us back to moving forward. And those are in our remote sensing systems, our models, our numerical weather prediction, that I think are contributing to their mystery and apparent unpredictability if we listen to the news, although I think this mystery is largely of our own making. So if we look at the progression of wildfire modeling over the past half century, a lot of this began in mechanical engineering, where fire science was invented as a discipline, in chemistry, thermodynamics, and engineering studies of flame and combustion. And that was looking at the fire process itself, largely in the laboratory and theoretical work. In the 70s, we've started seeing some work in wind tunnels and wind fire spread over fuel arrays in the wind tunnels, and some empirical formula, much of which we still use today, is used to describe how fast a fire might spread. The key factor over decades has been the rate of spread of the leading edge of the fire as a function of wind, fuel, and terrain slope. Refinements are made in some of these empirical formulas over the 80s to 90s, and extensions and alternatives. And those, as a group, we're looking at how fire responds to the environment. And some of these are still used today to predict the expansion of a fire perimeter. In the 1980s, we began to recognize that wildland fire phenomenon. There were things like fire winds within the fire much greater than the ambient winds, and distinguishing between plume versus wind-driven fires, fires that were driven by internally generated winds versus fires that spread fast because they were in a windy environment. But we were kind of stuck with the tools we had at the time. Simultaneously, there's been a lot of progress in weather modeling from the 60s to 70s, when early NWP was born. In the 70s, there was more expansion into studies of storms and precipitation. 80s to 90s, we really expanded our understanding of airflow in complex terrain. And that allowed us to make some progress in the 90s, where we could couple these advances in weather and fire behavior prediction, so that we could understand some of the basic aspects of fire behavior, like why a fire that starts in a line will bow into an elliptical shape. In these previous generations of models, that sort of behavior had to be parameterized, but here we could start to model this behavior as evolving from the fire dynamics itself and how the fire interacts with its atmospheric environment. But progress hasn't stopped. Weather modeling has been developing work in predictability, uncertainty, data assimilation, and in the some of the other tools and areas that are really expanding in recent years have been in machine learning, the appearance and integration of UASs into fire suppression, monitoring. There's been a huge expanse in the private sector. Previously, a lot of this work was done in national labs and in the agencies, but now there's been a huge investment in technology from the private sector. And there's been a great democratization, I would say, of information, both in fire detection from private sector constellations and so forth. So the things are still changing a lot, and there's expansion into other disciplines. This used to be controversial, but not so much anymore. The wildland fires are complex weather and fluid dynamics phenomena. All these aspects we can these phenomena we see in fires, from its shape to these phenomena that arise from dynamic interactions between a fire and its atmospheric environment. Many of these have analogies in severe weather, so they're things that we thought we could weigh in on when we saw them in fire, and that wasn't being taken into account by the forestry community, where the fluid dynamics aspect wasn't as strong. When we look at wildfires by the numbers, it really is dominated by a few extreme events. Only a few percent of them exceed 100 hectares. And the largest 1% of fires account for 80 to 96% of the area burned. When we looked over the historical satellite record for burned area, the days with very large daily fire growth are really infrequent, only a few days a year. And these might account for 35 to 77% when we were looking at California's burned area. So a very few fires account for most of what people would call the mega fire problem. And I tend to think of this not as an individual factor, but my hypothesis that I carry around and I test against events this year was that this results from a multi-scale coincidence. It's not just drought, although one component is an underlying susceptibility. This year, there was a low vapor pressure deficit over the Pacific Northwest, so they saw most of the fire activity this year. But on top of that, there needs to be a local period of locationally specific weather that can spread the fire. And that might be externally generated winds, like wind events, or it might arise from the dynamics of the fire. And you need a fortuitous ignition at the right place and time to take advantage of it. So this makes it a complex, multi-scale problem that is being worked on by a number of groups. Ecologists, foresters, others that come from a life science background, but those of us here, we come from a physical science background, so we have different tools at our fingertips. We look at mechanisms for these days of extreme fire growth. Most of these fires occur at the either end of a spectrum. That is, they're driven by externally generated winds, or they occur during weak wind environment, but the winds from the fire, which could be 10 times stronger than ambient, are generated by the heat release from the fire itself. Of course, we have some exceptions. The last couple of years have generated some fires that have both plume-dominated components and wind-driven components. One head of a fire might be driven by external winds, and another part of the fire might be generating its own winds. And some of the largest fires, for example, the Dixie Fire in 2021 that went on and on and on, started as a plume-driven fire, then it encountered a wind event, and then it was driven down into this east side of the Sierras, where thunderstorms kicked it around for several more weeks. So these weather patterns can stack up and generate fires that go on and on and on, generate the large complexes. But I think an important aspect is that these appear mysterious because these extrema are the weakest links of the current tools, both because the current tools don't include the ability to model these internal dynamics, these fire-generated winds. And at the other end of the spectrum, there's a lot of unknowns about the microscale extrema in the winds that are being generated in some of the California wind events. So these look mysterious because of our gaps in understanding in a couple ways. And the current tools can't really address either of them. The tool I use is combines a numerical weather prediction system, numerical weather prediction model with a package of fire behavior algorithms, but those fire behavior algorithms are very similar to what's been used over decades. These this package of tools interacts with the numerical weather prediction model at every time step. So we're modeling the airflow over complex terrain, second by second, and as it varies in time and space, it's driving the fire to spread and consume fuels. But as fire consumes fuels, it releases heat into the atmosphere, generating a plume, and the plume pulls in air at its base, shaping the fire behavior. So this interaction is really the difference from what went before, rather than the details of the fire modeling itself. So I hope we have a lot of fluid dynamicists in the audience. Can you raise your hands? Oh, good. Okay, well, I think there's a lot of details about the numerical weather prediction that are key to our advance. So that's why I was hoping to stir some students into interest in this area, so we can make those advances. A numerical weather prediction model. This solves a set of partial differential equations. These are physical laws expressed for a fluid. These have to do with the Navier-Stokes equations of motion, that conserves momentum, the law of thermodynamics, mass conservation, the ideal gas law. These are all things that we can understand as physical scientists as natural laws, and we write them in this form to describe how fluids must behave. The continuous form of some of these equations and flux form is in the upper right. The first is the prediction of how momentum changes due to pressure gradients, buoyancy effects, stresses in the gas itself and from the surface, that we expressed in the second equation that mass must be conserved. And the third is a predictive equation for how scalars might change. And that would be from sources and sinks, and also diffusion and some other sources. This particular model I use, well, let's say there are different solution methods that you might use for modeling fluids at different scales. Although all our fluid models solve these equations, the ones that do it at synoptic scales keep different terms than the ones we're interested in fine scales. For example, we're not really interested in the Coriolis force for our fine scale short duration simulations. And these can have a big impact on our solution. We use an inelastic approximation, which ignores buoyancy gradient or density differences, except as it contributes to buoyancy. Other solution methods were used for the Whorf community model, which uses a compressible formulation. There are different properties that impact our solution. For example, the inelastic approximation filters out sound waves. It has properties that it identically conserves mass, whereas if you're using a compressible formulation, you don't identically conserve mass, and that has implications, but it does conserve energy. So these are all trade-offs. We choose an appropriate one for the scale we're working at. There's also approximations we make when we discretize them that impact our solution. For example, this model contains a formulation Peter Smoller-Cavage came up with to preserve large scalar gradients. That's important for wildfires because it starts off as a gradient between the hot area of the fire and cooler air outside of this. And this temperature gradient has to fight its way up scales to develop pyrocumulus and so forth. So depending on your problem, there are many decisions that have been made for you if you're using another model that could impact your solution. I've described some of those in a publication I listed at the bottom. And the details for the model are described in a tech report here. The fire behavior package, this is a conglomeration of other things that have been used by other people in, for decades. We have to represent and track an interface between the burning and non-burning region of the fire. We call it the flaming front. This whole fire might be within one of our grid cells. So this is keeping track of an interface between our cells, not something that our cells resolve, our atmospheric grid cells resolve. We track how fast it spreads according to semi-empirical relations. We also keep track of the heat release behind the front because fuel, once it's ignited, might take some time to consume, and that determines how much heat in the form of temperature and water vapor are released into the atmosphere. And then we release these into the lowest layers of the atmospheric model. If there's a canopy overlying the fire, it might catch on fire and spread a crown fire. And we also have semi-empirical relationships that tell us how fast it dries and how fast it spreads the fire. So we're not looking in detail at combustion, but we're representing these processes, and what our atmospheric model sees is how these fluxes change over space and time. Tracking this interface, this is excessively detailed, but I just wanted to show you we keep track. This is an ad hoc method, something like the particle and cell method, where we keep track of cells, fuel cells within the atmospheric cell, and we keep track of how this interface spreads by looking at tracers, 4 tracers on each one of these grid cells. So we keep track of how fast they spread perpendicular to the interface at every time step. It's horrible, ugly code. This coupling allows us to integrate these. Compared to the previous generation of models, this coupling allows us to combine these effects of these various environmental factors and show how they amplify and reinforce each other through the atmospheric medium. So in the previous generation of models, the rate of spread, you just calculated at points along the fire line as a function of wind, which you would have to estimate without the effects of the fire in the local slope. And you calculate the rate of spread and how fast that's going to expand outwards. But in a coupling framework, the wind blows across the fire line, it releases heat, which pulls wind across the fire line, which creates more heat and spreads the fire and allows it to create these interactions that amplify and lead to things like blow-ups and firestorms, what the engineering fields would call the mass fire effect. If we're going to simulate a particular event, how do we do this? We're modeling the weather over a large portion of the country, maybe the western US, and we're initializing the weather with weather analyses. We're looking at the past, or a forecast if we're looking at the future. The other data we might bring in is terrain elevation data and a fuel map, that an example of which is on the right. These are stylized categories. The basic data set for which is land fire, and nearly everyone uses it, although other data sets are coming online, and along with information about the fuel conditions. And we bring in information about the fire and allow it to ignite in this running model at the time and location it was observed. That might be at the ignition of the fire or when we have an observation from some sort of remote sensing. So we start our weather model running coarsely. We refine down to hundreds of meters, which is an order of magnitude finer than national weather forecasts are done at. So we're looking at a particular valley where a fire occurred, and we're modeling that at hundreds of meters grid spacing in often a terrain that's, might be 30 or 40 degree elevation. So it's at the edge of what numerical weather prediction can do in complex terrain. Just a quick snapshot of the fuels. We're trying to represent very different fuel categories on the surface and in the canopy. These might be grasses, very fine scale grasses, to larger fuel particles that can still spread the fire. These fuel particle size determine how fast the heat released. Whereas tall grass is consumed very quickly, maybe in less than a minute, these slower burning larger fuel particles might release heat over a half an hour or hours. And that leads to a very different fire. For example, on the right, the upper fire represents what a flashy fuels create, a very fast moving fire with high heat release over a narrow region, whereas slower burning woody fuels release heat slowly over a wider region, creating a slower fire with a deeper burning area. And these have impacts consequentially on the dynamics. The type of data we have to initialize the fire in progress, we used to, it was really difficult, but since 2012, we've been getting data from the visible and infrared imaging radiometer suite on Suomi MPP. So at least twice a day, we would have an observation, much like the center figure, that was high enough resolution to delineate the fire front, whereas MODIS wasn't much use. It was too coarse for this type of data. And since then, other types of data have come online. We would use this to initialize the fire in progress in a running model. And we could also, for the first time, have data wall to wall that we could use to verify data. We used to have to track down the fire behavior analyst and get an image of where he thought the fire was at later periods. So that was an advance in modeling as well, the ability to verify it routinely for any fire, not just fires of significance. So how do we do this as a prediction sense? As a numerical weather prediction problem, they had several issues. One was that we needed to do fine scale simulations because the fire was driven by meteorology at hundreds of meters, finer than our numerical weather prediction models told us. And the skill at these finer scales decreases much quicker. So if I start a simulation, it might be good for a day, maybe not more than 2 days. We also had firefighters out there interfering with the fire. So what we were modeling is natural evolution. And there were some processes in the fire like spotting, the lofting of embers ahead of the fire, which we might be able to do probabilistically, but we couldn't do well with our deterministic models. So we expect our skill to go down quickly. So we had to adapt the process of cycling, what's used in the national forecast centers, as a paradigm for doing forecasts. So we might do a simulation. This is a fire in New Mexico from 2002, the Little Bear fire. So we might start our weather model running, would initiate the fire with the VIIRS observation, and time is moving to the right. So the next column is 12 hours later. That's our predicted perimeter. The next column is 24 hours later, and then the last column is 36 hours later. So the purple filled figures are the image of the fire from VIIRS. So if we compare our simulation to what actually happened, we see we had pretty good forecasts for 12 and 24 hours, although C on the first column is expanded too much to the north and south compared to what actually happened. And by 36 hours, our simulation is out to lunch. But that didn't have to be the end of the story, because 12 hours after our first simulation, we had a new observation, and we would have updated weather reanalysis and forecast. So we could start our new forecast running with a new observation and simulate from there, giving us a good prediction for 12 and 24 hours. So in this way, we could bootstrap through the life cycle of a fire from the time it was first observed until it was no longer detected by our satellites, and have a good forecast for the next day or two, which was a huge advance. We thought we had the problem solved, but of course we didn't. because there are gaps in our observations and other problems. But first, let's talk about what constitutes a good fire behavior simulation. And I think it's different by 2022 standards than it had been in the past, and that hasn't necessarily filtered through the field. People used to be interested only in an objective assessment of the expansion of the fire perimeter. How fast does the fire expand? This has always been easily gained. We call it calibration, but it's what we would science more call fudging, because it's ad hoc and it's done case by case basis with no standard. You just figure out how you need to fudge the inputs today to get a better answer, and then we use that same fudging tomorrow. It's been historically recommended, but it's kind of filtered into our physical modeling today, and a lot of that is going on in the background. So you should always question that if you review a fire simulation paper. I think there are other factors. Now that we're looking at coupled models, we can combine subjective and objective valuation of the shape of the fire, how it turns, splits, accelerates, where it blows up, where it produces flank runs, and these distinguishing features. So we can be much more picky about what we call a good simulation. We see things like multiple plumes along the heading region of some fires like the Yarnell Hill incident, where it had two changes in direction, where it might split into plume-driven and wind-driven heading regions. We can be much more picky about these very specific factors that go on during an event. We can also look at some of the phenomena a fire should be producing. We've had much more success in recent years producing where large fire whirls are going to form, where pyrocumuli are going to form and penetrate up into the stratosphere. All of these things that result from fire atmosphere interactions that we couldn't generate with the previous generation of models. So when we look at wildfire events, these wind-driven events that have been so catastrophic in California, meteorology community is pretty confident in its, perhaps not appropriately, but it's confident it can model wind-driven events, at least at the regional scale. When we try to understand what goes on when airflow goes over complex terrain, we talk about different flow regimes, depending on factors that include the steepness, the aspect ratio of the terrain, the wind speed over the top, the stability of the air being lifted over. A variety of factors can occur in the airflow in terms of vortices that curl around and might go over the top, it might split, it might go down the back. All of these are a combination of those environmental factors. And we thought those might apply to some of the wind events in California, some of which occurred during strong downslope wind events. The epitome of that would be some of the downslope windstorms we'd studied in from the 1970s in Colorado, but where we had waves coming across the Continental Divide where the air was stable, it would be lifted up and come slamming down on the lee side and generate 50 or 90, 100 mile per hour winds that would rip our roofs off and so forth. But was that a good analogy for what was happening in California? And it turns out not. So we don't really have a good foundational understanding of the meteorology producing these strong winds in a lot of places across California. What they have is also a pressure-driven flow from high pressure inland trying to get to low pressure offshore. And that was described simply in the literature as coming down canyons and so forth, but there wasn't a lot of studies, certainly at high resolution, to understand what was going on. But a big picture is that the winds near the surface are coming from the northeast, heading offshore, but these rotate counterclockwise with height from the surface to the middle atmosphere. So there's a rotation in the winds. but not a critical level, as some people have described. The air is very stable for the lowest 1 to 1.5 kilometers near the surface, which causes a lot of flow effects when it's lifted over features like the Sierras. And of course, there's a lot of topography, varying topography. California has some very shallow, wide mountain ranges, but also some high and steep ones that cause different effects. And this combination creates unique flow effects we haven't seen elsewhere, particularly when they're driven by such high pressures that these winds are reaching 90 to 100 mile per hour hours. But unlike Colorado, they don't support vertically propagating waves. So one of those, the key one, was the North Bay firestorm of 2017. We'd had some large fires in San Diego, but this was a disaster of another level of magnitude people hadn't seen. So a lot of great deal of variability across California. This snapshot is of a box in the coastal mountains, including Napa, north of San Francisco. If we look at it, what was going on at various places in this boxes, there were pulses coming off these lower mountain coastal ranges over Santa Rosa. There are streaks of high winds. The higher winds are in hotter colors of red. To the north of this, there's some areas that didn't experience strong winds at all. And of course, there are pulses coming off the east side of the Sacramento Valley where other fires occurred. In this event, there were over 170 wildfires ignited in the wine country, in these northern coastal ranges, and 14 of them grew rapidly, some joining into multi-fire complexes. Go away. But so how do you understand what's going on there? Well, first you look at the mesonet, and it provided an unclear message about what was happening. This is a snapshot of the Tubbs fire, one of those fires that ran into Santa Rosa. If you asked a meteorologist where the strong winds would be, they would guess it would be on top of the mountain ranges. And to this date, the utilities are strongly emphasizing the mountain peaks as a location for sampling the winds. But in this case, I separated the winds measurements from the mesonets into stronger, medium, and weaker below the image here. The stronger measuring locations have squares, and some of them were indeed on top of these mountains, but some of them were also down in the valleys outside Santa Rosa. And strangely, if you were a meteorologist, they were sitting right next to other locations that had some of the weakest measurement. A station in the middle of the fire, which of course got consumed, had pretty low winds. So it wasn't clear by looking at the mesonet what was driving this extreme rapid spread of the fire, which in only a few hours covered, I forget, 10 to 12 acres from its ignition into Santa Rosa, leaving little time for evacuation. So what else do we have? We have tools that are from our weather models. WRF is the commonly available community model developed for mesoscale simulations, although people use it at a wide range of scales, from climate down to microscale simulations of turbulence with varying success. The WRF simulations predicted there would be downslope winds, but their peaks only reached to about 70 miles per hour. And it was obvious from some of the weather stations nearby, not the weather station, sorry, from some of the damage that occurred, that the wind damage was up exceeding 100, perhaps 110 miles per hour. So it seemed obvious we weren't getting a good picture of what was going on. And a consequence is why we're looking at the Fluid Dynamics Institute. I think there's a large role to be played in developing a dynamic framework that can better represent these types of events. The numerical algorithms in WRF vigorously suppress small-scale motions. So this is a figure I nicked from Bill Skammerock. So if you're, this is an energy spectra, how much energy is in eddies of different scales. So big eddies are on the left, and little eddies, tiny microscale things, are on the right. Nature adheres to a k to the minus 5/3 spectra, and when applied as a simulator of the environment, and we look at the energy spectra and simulations, WRF strongly deviates from that at fine scales. That's not unexpected, it must, but it's pretty severe. Based on the log scale, 90 to 99% of the fine scale motions that should be there in nature are missing in the fine scales of its simulations, and that's important for some of the meteorology we'll be looking at, but also specifically for the fire application, where fire starts as a fine scale gradient across a maybe 10-meter fire line and has to fight its way up scales to become the large fire events penetrating the stratosphere. So the details of the formulation of the model are extremely important, particularly in this application. So a digression, I have a few of those, or why you students should pay attention in numerical analysis class. This has important impacts on modeling certain aspects of atmospheric dynamics. For example, some of the fires we've had, the Hyde Park fire, are driven by atmospheric gravity wave breaking, and my simulation of that with the model designed for these types of simulations is on the lower right. But if you look at some of these simulations of wave breaking in papers that say they're modeling wave breaking, they're not actually modeling wave breaking. The model properties smooth it out. So you might get something that looks like a wave, but without modeling the dynamics, you don't get that pounding on the surface, which spreads the fire, and you don't really understand what is driving the event. If we model the Tubbs fire event, let's see, it's again in this box. So if you asked a meteorologist what the weather looked like on this day, he would expect that the strongest winds were on this mountain range, but instead the strongest winds are on some of these secondary peaks. Santa Rosa is in the lower left, and this is the evolving fire line. It was ignited when observed. So where the fire was ignited was on one of these little bumps in the lee of the range containing Mount St. Helena. But the peak winds there were bumped up another 10 or 20 miles per hour going over that bump. That's where the ignition occurred due to an interruption of the electrical grid. The hotter colors show the stronger winds spreading into Santa Rosa. The south end of the fire is being drawn up a ridge line. Oh, I don't want to do that. So we always compare our simulation with what actually happened. So captured many aspects of the event: a rapid spread, the strong winds at the ignition area, and the bulge out to the side drawing up this ridge outside of Santa Rosa. We have to be careful with the satellite data. It's not giving us a perimeter. It's just actually showing us a hot spot. So when we have embers, they can confuse our simulation. But if you're a fluid dynamicist, this is kind of fascinating. Our meteorological lore tells us that in this high-speed flow, it ought to behave like neutrally stratified flow, where our peak winds are over these ridges, and that was mostly true, but what we saw, there were these eddies that spun off these smaller peaks and down into Santa Rosa, creating these gusts, and the gusts were what bumped the winds up over the failure load of the electrical grid. So these microscale extrema, this particular weird effect that occurs in one hotspot, is something that we didn't recognize from our meteorological regional models. It doesn't show up in our mesonet data. So it's been hard to identify what is going on in these locations. Can be configured as a weather forecast. A very different effect at the north end of the valley, in the Redwood Valley fire. We were looking at tubs down here with the pulses. The northern end of the this event, there was an area outside Ukiah where there was a river of extremely strong winds. It was about 12 kilometers wide, and at the time it barely nicked some of the mesonets. So if you were looking at that area, you wouldn't necessarily detect that these strong winds occurred. And indeed, there were excessive winds in some of these locations that brought vegetation into contact with the electrical grid and started some fires. Again, this was a shallow, stable layer near the surface, and it created some of these pulses. So these are very fine scale effects. There's not a lot about this in the meteorological literature. So we kind of been blind about these small scale effects that we couldn't capture with our models and didn't pop up in our mesonet. So as part of this California project, we broke California into a bunch of different regions and looked at airflow associated with wildfires and a lot of these different events. And a lot of this has been building a framework to try to figure out what kind of risk am I susceptible to in my location, because the terrain is very different in the Sierras, which are steep compared to the transverse ranges down in LA. So a lot of this was breaking it down by aspect ratio. Some of these problematic areas associated airflows associated with fires were a question of whether the airflow went over the top of a mountain range versus through. And through might be notches and saddles, like the Redwood Valley simulation I showed you. They might be broad dips, or they might be river valleys, like the one that leads down into Ventura County. There are different, it turns out it's different if you have a wind event and it blows really strong, then you get a sloshing effect across the top of the Sierras down through Paradise, versus a moderate strength event, in which case the strongest winds might be in these very narrow river valleys, very narrow in the sense that they might be only a kilometer or so wide, and therefore beneath the resolution of our forecast. So there's a lot of uncertainty still in meteorology in terms of understanding the conditions that lead to flows that might interrupt the electrical grid. And then some other aspects I'll mention if I have a time. So the Woolsey fire, this was November 8, 2018, just how I would do this. I focused down from Southern California down to the area of the fire. There was an ignition in the Santa Susana Field Laboratory. So strong, stable layer near the surface. Going over a couple mountain ranges before it impacted the ignition site. And if you looked at the winds over, modeled winds over the ignition locations, there are these pulses that are plus and minus 4 meters per second. So another 10 or 20 miles per hour stronger than the background mean. So the gusts are very problematic in that they kick the winds up over whereas the mean winds, something you might get with your regional model, would indicate the situation is okay. When these pulses are created, they might bump the winds up into a point where it's a problem for the utility grid. So in this case, these are very flat mountains. The flow is very Bernoulli-like, just like airflow that accelerates over an airplane wing. But because of these, the stability going over the mountains, there are little pulses that might increase the wind. At the same day, and we always evaluate our simulation. That's a reminder to myself. On the same day, the campfire ignited on the west face of the Sierras, and a much steeper mountain range. It was ignited in extremely strong winds, interrupting the transmission lines. So here we're looking at the simulated winds near the surface and the heat flux from the fire, where hotter colors or higher wind speeds or higher temperatures. So if we look at the winds on this lava face, there are pulses of wind driving the fire down slope. We have a few satellite observations for evaluation during that period, showing the rapid spread of the fire. It was the ignition was at 6:15 or 6:30 in the morning, and by 10:30 the fire was entering paradise. So how do you generate a fast-moving fire like that? If we look at the airflow again, we had this strong, stable airflow over extremely complex terrain. In this upper left figure, the heavier winds, higher potential temperature is hugging the surface with less stable air above it. So the shallow, very stable air is about a kilometer and a half deep. It's getting pushed over the Sierras and also these smaller features. And at the interface between the very stable air near the surface and slightly stable air above it, peaks in the air are getting bumped up in the slower moving air above it, which slow down and come crashing to the surface behind it. This is a shear instability, is what we would call it in fluid dynamics. And if we look at the fluid, the winds that created on the right, these black bulges are pulses in the wind. So these are created by this airflow and pound the surface, bam, 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 every few minutes. That created those scallops, those pulses of air. And if you can't resolve that, then you can't generate what the fluid flow that brought the fire from the top of the mountain down through paradise. And if I were to, these are very small scale features. These only appear when you model at, okay, first the campfire was a hot spot. Some of the other researchers disagree, but this was an area that was much stronger than anywhere else during this regional wind event. And you only capture this when you look at very fine scale flows. And if you don't capture this with your model, then some of these other simulations with WRF, which I said was more diffusive, leave the fire sitting on top of the mountain. Not just that day, but even at the end of the next day, they wouldn't have brought it into town. So this is an area where computational fluid dynamics and the ugly details are extremely important for developing models that make good prediction tools. Because some people want to implement this as a forecast tool, but if you were sitting in your home, it would tell you, stay at home in your home in paradise. You're perfectly fine. The fire won't get to you today or even by the end of next day. And I think that's tremendously dangerous and reckless. I don't want to keep you too much longer. There are different airflows, like this is the same river valley, but a different event, the north complex. So winds on the downslope faces, but in this case, it hugged the river valley and it was more like air was being sucked down into it. So it's a different effect in the same location by different conditions. I guess I don't want to keep you long. So when we look at the WUI problem, a lot of the issues are with embers, and NIFC thinks of it as this, a plume lofting embers, which can spread the fire faster. But the real problem is that the fire-induced winds create the plume, and the houses aren't just igniting or creating the embers, but they're being ignited from them. So we're trying to understand whether this heat from the fire can affect the atmospheric dynamics. So it kind of rigged this little test of WUI fires. On the event you looked at, I showed you the Tubbs fire simulation. And if we include the effect of houses on the dynamics, they're different from wildland fuels, a tremendous heat release, but it's over a much longer period of time. So a lot of the emphasis and research is on WUI fire. So what would this have done to our simulation? By having all this heat release in these communities along the edge of the mountain range, we would have done a better simulation, because all that heat release creates a plume that creates a backflow, slowing the fire spread down. But it also creates features like these fire whirls that were observed in those communities. And these are important because the rapid spread of the fire whirls increase the destruction. We could create events like the car fire, these fire whirls. Let's go to our conclusions. So some of the firefighters are interested in things like the Marshall fire that occurred outside Boulder. I modeled the event. It was an ignition during a wind event. That's the fire to the south here. But there was an earlier event, ignition north of Boulder, called the Middle Fork fire that they put out quickly. I modeled the event as if it had not been put out. And just because of where it was located in a region of more consistent, strong winds. This was a day when we had 103 mile-per-hour winds measured at some of our wind events on December 30th. The fire that was put out would have, as bad as this southern fire was, spreading into Superior and destroying 1,000 homes, the one that they put out would have caused much more damage, swooping across northern Longmont. So as bad as the day was, it could have been a lot. It could have been a lot worse. So we're using these events to try to understand what could have happened. We don't have a lot of that in the fire community. A lot of these are weird circulations. I'll show you the creek fire and then I'll quit. So this was a really odd event. There's a lot of mystery about what causes a fire to behave the way it does. And the creek fire was an extremely deep pyrocumulus event that occurred during weak winds outside Merced on the west slope of the Sierras. The rapid response from the community was that it must have been due to these high mortality fuels due to beetle kill in the Sierras. But using the standard fuels, we could look at using the standard fuels specification in our, I'm not doing that. You go. If we model the, okay, you're not going to go. So the spread of this fire, it was really rapid up the San Joaquin River Valley in a way that was really unexpected. People attributed it to the high mortality fuels. But looking at this event, we can generate this strange airflow that developed just because of the specifics of the location. The fire generated updrafts that were over 30 meters per second, and there were a series of updrafts circulating around. They're indicated in red up here, in between this wall of downdrafts. So much like a hurricane circulation, the fire generated this mesovortex because of the strange combination of winds and topography. And we've seen a number of them since in other locations. So a lot of the understanding about why wildfires behave the way they do arises from misattribution. We've been fudging our models for so long with this calibration that nobody really understands what causes what. And I think that's also extending into understanding of whether we're at risk of more large fires or not. It's based on a misunderstanding of why fires behave the way they do. And I think it's all based on this fudging. So I tossed this out for the community. We're trying to develop other types of models and the introduction of machine learning. One of the challenges, I get a call all the time of people who want to use mesonet data to predict fires, with the understanding that with the thought that if we measure enough, we can predict fires just knowing what we do with the environment. And this really hasn't been successful in trying to understand large fire growth. I mean, if you look at burned area, you can only explain 25 to 50% of the variability from the mesonets, and you can't really use it to understand individual events. A lot of that is because of the microscale variability and that these winds are generated from the fire. But I know there's a lot of work going into machine learning and using that to predict fire spread. But this is kind of a conundrum that we're at as a community. So I'll stop there since I've gone on far too long, but I'm interested in if you have questions on understanding events, but also what you think the potential is for developing these fluid dynamics models to investigate the fire behavior more accurately in ways we haven't done as a community to date. So thank you very much. I don't talk to anyone for a month at a time, but then when I do, I just go on and on and on. So happy to take questions.